Hi, this is Rachel Sue, and today we will be going over problems in chemical kinetics, specifically how to determine the order of reaction from observations. The problem reads, indicate the order of reaction consistent with each observation. A plot of the concentration of the reactant versus time yields a straight line, and B, the reaction has a half-life that is independent of the initial concentration. Let's first look at part A. Here's a visualization of what the plot of concentration versus time would look like. Time would be on the x-axis, and the natural log of the concentration of the reactant would be placed on the y-axis. The slope would be a straight line with a value of negative k. We know that if this graph yields a straight line, then the integrated rate law in the form of natural log of a t is equal to negative kt plus natural log of a0, where a is the concentration of the reactant, k is the rate constant, and t is time, would fit a linear format of y equals mx plus b. This indicates that the reaction follows first-order kinetics. If the graph were to yield a curved line, then this would not be first-order kinetics. Therefore, the answer to part A would be that first-order reaction would be consistent with this observation. Next, let's examine what the order of reaction would be if the observation is that the reaction has a half-life that is independent of the initial concentration. Half-life is a measurement of how long it takes for half of the sample to react. In the first equation, AT is equal to half of A0, where A0 is the original compound and we are trying to find how long it takes, as indicated as T, for the concentration to reach half of the original A0. We can then take the integrated rate law in the format of natural log of AT divided by the original concentration is equal to the negative rate constant multiplied by the time, and then we can plug in the numbers to get natural log multiplied by 0.5 of the original compound divided by the original compound is equal to negative 0.693, which is also equal to the negative rate constant multiplied by time. We can then solve for time to get 0.693 divided by the rate constant is equal to the half-life of the reactant. For first-order reactions, the half-life of the sample is always independent of the concentration, so what determines the half-life is not the original concentration, but the value of the rate constant k. The larger the value of k, the shorter the half-life. Therefore, the answer to part B would be that the first-order reaction would be consistent with this observation. To summarize, when solving problems like this, carefully consider the information given in the problem to see if it's consistent with properties of the first or second-order reactions that we already know of. For first-order kinetics, a graph of the natural log of concentration versus time will yield a straight line, and the half-life is always independent of the initial concentration. If these properties show up in the problem, then we know that this would be a first-order reaction.